Okay, in this video, we're going to start back into our previous topic on exponential functions, and we're going to talk specifically about how the graph of a function can be transformed when you modify its equation. Okay, so to do that, we're really basically going to look at two learning objectives. For those learning objectives, the first one is going to be simply to know some rules. Okay, so the way that we're going to approach this process of transformation is by looking at some rules. And in this particular video, we're going to look at 3 rules altogether. So you're going to need to know the rules, and then once you know what they are, you're going to need to apply the rules. Okay, so that's really what we're doing. But before we get into that, we are going to start with just a very quick review on working with exponential functions. Okay, and to do this, what we're going to do is we're going to make a graph. Use a table. Whoops, that's not how you spell table. Table to graph y equals 2 to the x. Y equals 2 to the x. Okay, now when we did exponential functions the last time around, we didn't actually use tables to make graphs. We approached it a slightly different way, but everything that we're going to do in this is something we've learned how to do. And so that's why I call it review, even though technically speaking, we didn't do this before. So the first thing that I'm going to want to do is make my table. Okay, so I've got x and then y equals 2 to the x. And the table values that I'm going to use, -2, -1, 0, 1, 2, and 3. Those are the values that I'm going to use. All right, so remember the way this works is I'm taking my exponential function, and these are the numbers I'm going to plug in for x. So for example, when I plug in a 3 for x, then I'm going to get y equals 2 to the, and then right here the x becomes a 3. And 2 to the 3rd power, we know that means 2 times 2 times 2. That's what 2 to the 3rd power means. And so the answer that I end up with is 8. 2 times 2 is 4, times 2 is 8. Okay, so that's a little long process. But what that does, though, is that gives me 2 pieces. That gives me an x number and a y number. And so when I take those 2 pieces together, now I have an x number and a y number. That gives me an ordered pair that I can graph. Okay, so that's my basic process, and I need to do that for all these numbers. So maybe what you should do right now is pause the video and figure out what are the y coordinates for all of these x numbers. All right, so hopefully you found all those y values. Again, for each of them, all you're going to do is plug the x number in where the x goes, and then simplify what you get. 2 squared equals 4. So for this particular one, my point would be 2, 4. Okay. Likewise, if I plug in a 1, I'm going to end up with 2 to the 1st power, which is 2. When I plug in a 0, I'm going to get 0 for x. 2 to the 0 power, well, everything to the 0 power always equals 1. So there's what I get there. Okay. Continuing along, if I plug in -1, remember what negative signs do is they make fractions. So I take the answer I got when I plug in +1, which was a 2, and then I just find its reciprocal. So the reciprocal of 2 is 1/2. And so that's what happens when I plug in -1. Or the other thing you could do is look at your pattern. 8 to 4, I divided by 2. 4 to 2, I divided by 2. 2 to 1, I divided by 2. If I take 1 and I divide by 2, I get a 1/2. So however you want to find that answer, but you need to be able to get all of those numbers. Okay, so that's the first thing. Just simply plugging these numbers in for x, and then simplifying what you end up with, making sure that you remember that anything to the 0 power always equals 1. And when you have something raised to a negative power, that creates a fraction. All right, but now that we've got all those coordinates, we can make a graph. So I happen to have a piece of graph paper handy right here. And all I'm going to do is I'm going to plot those points. So I had a point at -2, 1/4. So there's a point there. I had a point at -1, 1/2. I'm just reading these right off my table now at this point. I had a point at 0, 1. And then at 1, 2. At 2, 4. And at 3, 8. And so those are the points from my table, right? So all I did was I just read those right off my table, plotted those. All right, now, one thing to keep in mind that as the graph goes down here, it doesn't keep going down forever, right? We know as that exponential functions have asymptotes, so this is going to continue to curl and flatten out. And so I end up with a situation where the x-axis is an asymptote. So don't forget to make that a part of your graph. It's a little bit hard to see when it's on the x-axis, but technically it's there. Okay, so don't forget that that's there, right? The x-axis is an asymptote. And remember, the equation for the x-axis is y equals 0. And that's our horizontal asymptote. Okay, now all that's left then is to draw on my graph. So my graph, it's curling up through these points here. And we know it's just going to keep on shooting up higher and higher and higher. And it's curling down through these points the other way, but here it's going to curl down and flatten out along the x-axis because that's an asymptote, right? Which means it's getting closer and closer to it, but it never actually touches it. And so there's my graph of y equals 2 to the x power. All right, so when we studied these before, we talked about the graphs and we talked about how to plug numbers into an equation to get y values. We talked about all these bits and pieces, but we never actually wrote or went through the process of finding the whole graph last time. Okay, so in a sense that's review, but in a sense that's new. Now the reason why that's all important is, again, going back to our learning objective, we're going to be transforming graphs, modifying graphs. And so it's going to be important that we have a graph that we know so that we can then turn around and modify it. Okay. Now what I'm going to do, I said, is we had 3 rules. I'm going to go through each one of those 3 rules, and I'm going to explain what the rule is first, and then I'm going to modify this graph. So I just happen to have several copies of this graph sitting here. Okay, so I've got, when we get to that, I can just reuse that same graph over and over and over again. All right, you will probably need to, when we get to each one of those points, pause the video to draw that graph to help you. All right, so here we go. Our 3 rules. Okay, our 3 rules for transforming graphs. The first rule, and by the way, you do not need to know the names of these rules, but the names are very straightforward in that they tell us exactly what the rule does, exactly what it does. So the first rule we're going to look at is the rule for a vertical translation. Okay, now if we take those 2 words, we know that vertical things go up and down. So this is a transformation that makes things go up and down. And a translation, if you think back to geometry class, translation means that something is just scooting, it's just sliding. It's just moving across the graph in a very uniformed way. Nothing is being stretched or twisted or flipped, or it's just scooting around, okay? So what I'm going to have is something that's scooting up and down. It's sliding either up or it's sliding down, one or the other. That's a vertical translation, vertical translation. So this rule has 2 parts to it. The first part says that a graph will move up when a number is added to its equation. Okay, so that's the first half of the rule. The second half of the rule says the graph will move down. Whoops. The graph will move down when a number is subtracted from the equation. Okay. All right. So all of the rules are going to have this same basic structure to it. There's going to be something that's changed in the equation. In this case, we're either adding or we're subtracting a number from the equation. And then that's going to cause the graph to change in some predictable way. In this case, either the graph is moving up or it's moving down. All right, so that's basically how all the rules are structured. Now let's make sure that we understand what that means, okay? So I'm just going to draw a random generic graph, okay? So this is not any special exponential function. In fact, I'm not even going to give it numbers. I'm just going to use all variables so that it can literally be any exponential function. Okay, y equals b to the x, just any random thing. And y equals b to the x, it has all these points on it all along, okay, wherever they're at. I don't know, I'm not giving them numbers, but it's got all these points, okay? So what happens is if I take this equation and I add a number to it, like y equals b to the x plus 2, let's say, okay? If I do something like that, then this says it's going to cause the graph to move up. If you add something to the equation, the graph moves up. So every one of these points will move up 2 units from where it is. And so what you end up with then is a new graph that's up higher, something like that, okay? Now, remember, this graph flattened out along the x-axis. So all of these points along the flat part, all of those points are also moving up 2 spots, which means this new graph is going to flatten out, but it's not going to flatten along the x-axis. It's going to flatten out at some spot that's 2 up. That's where it's going to flatten out. So in a vertical translation, the whole graph, including the asymptote, is going to either slide up when I add a number or slide down when I subtract a number, one or the other. So this is the basic idea of our first rule. All right, so let's actually do that. So here's our graph, y equals 2 to the x. This is the graph that we just made a second ago. What I would like to do right now is figure out what will the graph of y equals 2 to the x minus 6 look like. Y equals 2 to the x minus 6. So I've got my original equation, 2 to the x. That entire equation, I'm subtracting 6 from it, okay? So first of all, it's subtracting. So if I look at my rule, subtracting causes the graph to move down. So each one of these points is going to move down. How far is it going to move? It's going to move down this far, 6 units, okay? So if I was up here at 8 and I go down 6 units, there's 1, 2, 3, 4, 5, 6. Now I'm right here. So the point that was at 3.8, now that point is at 3.2. Okay? This point here that was at 2.4 is also going to move down 6 units. 1, 2, 3, 4, 5, 6. So now it's down here. So the point that was at 2.4, now it's at 2, -2. Okay? Likewise, I'm not going to do this for every single point. Let's just jump to this one. It was at 0, 1. If it moves down 6, 1, 2, 3, 4, 5, 6, now it's down here at 0, -5. Okay? These points are also going to move down. So they're going to go down, but they're moving down some fraction. So it goes down 6 units. So it was up a half, now it's down a half, 2 halves, 3 halves, 4 halves, 5 halves. There's my 6 units going down. There's my 6 units going down. So it's gone down to -1, comma 1, 2, 3, 4, 5.5. Okay, -5.5, -1, -5.5, something like that. Okay. Now, again, that's going to happen for every single one of these points. Every point is going to go down. So that means the asymptote that I had here, that asymptote is also moving down 6 units. So it was at 0. If I go down 6 units, 1, 2, 3, 4, 5, 6, now I'm down here at y equals -6. That's my new asymptote. And so if I connect all these dots together, I end up with something that looks like that. Okay, so this is the basic idea of all the types of things that we're going to do. And because they're all very similar, as we look at the next 2 rules, I'm going to go a little bit faster with them because it's the same basic idea for each of these rules. I'm going to take the graph that I know, and I'm going to change that graph somehow or another to make a new graph. Okay, so one thing to be aware of with this new graph, you should be ready to talk about the new graph. Like, for example, what changed in the graph? Well, the only thing that changed were the y numbers got smaller. If the only thing that changed were the y numbers, then that means the domain should be the same, right? Because domain deals with x numbers. So the domain should be the same. The y numbers all shifted down. So my range isn't going to be the positive numbers anymore. Now my range is going to be the numbers that are bigger than -6. Okay. My asymptote moved. So now my y equals 0 is no longer my asymptote. It's y equals -6. It's my asymptote. So again, just like we had before, you should be ready to talk about these different types of graphs. Okay. So there's our first example with actual numbers. Getting ready for our second example here. Rule number 2. Rule number 2. Rule number 2 is a horizontal translation. Horizontal translation. So this one also has 2 parts. And you can probably guess from the name that the 2 parts are going to talk about the way the graph moves to the right and the left, right? Translation means it's moving. Horizontal means either right or left, okay? Now, this might be a little bit counterintuitive when I write the rule if you really think hard about that. But again, right now, we just want to make sure we know the rule. So here's what the rule says. A graph will move right when a number is subtracted from the x in its equation. Okay. Now, before we moved up when we added a number, and we moved down when we subtracted a number. In this rule, we move right when we subtract the number. And the second half of the rule is the graph will move left when we add a number. Okay, so now we're moving left when we add a number. Okay, so those are our first 2 rules. Now, just like before, a quick sketch with something that doesn't have any numbers, just a general idea. Okay, so y equals b to the x. What does it mean to add something to the x? Okay, so what it's going to become is something that looks like y equals b, and then it would be x minus some number, and that number would be up in the exponent. Okay, that's the idea, is instead of adding it to the whole equation, we're just adding it to the x up in the exponent. So that makes it move to the left or to the right, depending on whether they're adding or subtracting. In this case, I'm subtracting, so it's going to move right. So what's going to happen is for every single point on this graph, and again, doesn't matter which points you pick, all of them, the point is going to move 3 units to the right in this case. And so you end up with this new graph that goes something like this. Okay, something like that. All right, so that's the basic idea to this. Now think about the asymptote on this one. The asymptote is the x-axis, and which means it's a line that goes forever to the right and left. If I take a line that already goes forever to the right and the left, and I slide it to the right a little bit, don't I really just end up with the exact same line? Okay, so when we're doing a horizontal translation, my asymptote's not going to change. And I'll let you think a little bit about, you'll have questions in the homework. Well, what about the domain? What about the range? Will they change? Okay, so that's something to think about, and you'll have to work with that in the homework. So here we go. There's my equation. What I want to do here for this second example, and again, you might need to pause the video to make a graph here real quick. But what I want to do is make a graph of y equals 2 raised to the x plus 4 power. 2 raised to the x plus 4 power. Okay, so maybe pause the video, think about that for a second. All right, let's talk about graphing this. So if we go back to our rule here, the rule says that when we are adding things to the x, we move the graph to the left. And I mentioned when I wrote that that might seem counterintuitive. So let's think about this for a second. If I'm going to move 4 units to the left, 1, 2, 3, 4. The point that was here at 3, 8 is going to end up over here. Now, where did that end up at? It's still up 8, but now it's over -1. Okay. Here I was at 2. If I'm going to move 2 units to the left, 1, 2, 3, 4, 4 units to the left, excuse me, I missed a vote. I end up at -2, but I'm still up 4, right? When this point moves over. When this point moves over. So notice what's happening, and this is the part that's a little counterintuitive. In the equation, I'm adding 4, but on the graph, I actually end up subtracting 4. If I'm at 1, I end up at -3. Okay, so that's the piece that's a little bit strange. It's a little bit counterintuitive. Some people just need to take a little time to get used to that, perhaps. But I end up with this graph. It still has an asymptote, but now the graph goes up like this. Okay, now it is eventually going to hit the y-axis. Remember, there's no vertical asymptote here. In fact, this one, if I plugged in 0, I would get 2 to the 4th power, which equals 16. So I'm going to hit the y-axis at 16. There's 8, 9, 10, 11, 12, 16 would be way up here. Okay, so you don't necessarily need to make that a part of your graph. I just want to make sure that we realize that it does eventually get to a y-intercept, right? There is no vertical asymptote on these, only horizontal. All right, so that's the idea of a horizontal translation. My whole graph just scooched over to the left 1 unit. Okay, that brings us to rule number 3, our final rule. Rule number 3 says this. Well, first of all, the name of it is a vertical reflection. Okay, now this is a little different. Vertical still means that we're moving up and down. Reflection, thinking back to geometry class, that means something is flipping. Okay, so if I have something that's flipping vertically, if it starts like this and I flip it vertically, the stuff that was at the top now becomes at the bottom. Okay, so that's the idea of a vertical flip, is that I've got something that goes from here to being here. Okay, that's the idea of a vertical reflection. So this one doesn't have 2 parts to it, which is nice, which is convenient. The vertical reflection rule says this: a graph will reflect vertically over the x-axis. So the x-axis is going to be our mirror, right? That's what that means. The x-axis is going to be our mirror. The graph will reflect vertically over the x-axis when its equation, so we're working with the whole equation again, not just the x, when its equation is multiplied by a negative number. By a negative number. Okay, so that's our rule number 3. So again, to just talk about it generally here real quick, what that means is if I have a random graph that goes like this, then if I want to multiply the equation by a negative number, that would look like this, right? Multiplying the equation by a negative number. That's going to make it flip over the x-axis. So the stuff that was a little bit above the axis, now it's a little bit below the axis. And the stuff that was far away, now it's far away but down below. And so I end up with a graph that kind of curls and goes like that. Something like that. That's the idea of a vertical reflection. The things that were up high, they are now down low. Okay, that's the idea of what's going on here. All right, so let's finish our notes and finish this video by taking a look at an example of something that's a vertical reflection. So if I take y equals 2 to the x, and I want to draw a graph of -2 to the x, y equals -2 to the x, okay, what that's going to do is it's going to take each of the y values and flip them down below. So if I was up 8 and I flip it down below, now I'm going to be 1, 2, 3, 4, 5, 6, 7, 8. Now I'm going to be down 8. I'm still over 3, but now I'm down 8. Okay, same thing if I was up 4 right here. Now I'm going to be flipped over the x-axis. So if I was 4 above the x-axis, now I'm going to be 4 below the x-axis. Okay, and that's going to be true for all of our points. And I'm going to, for the sake of time, not necessarily graph every single one of them, but there's where we are. Okay, or at least not label every single one of them. So you can see I still have this asymptotic behavior, because if I have an asymptote and I hold it up to a mirror, the asymptote's still there. It doesn't go anywhere. It just is asymptotic on the other side of the mirror now. Okay, so I still have the same asymptote, so that hasn't changed. None of my x values changed, so they still have the same domain, but all my y values just became negative. So maybe if you think about this, it seems to me that our range has changed. Our range used to be the positive numbers. Now the range, maybe it's the negative numbers. Okay, all right, so this is the basic idea. 3 rules in reverse order. Doing a vertical reflection, it happens when you multiply by a negative. Then rule number 2, doing a horizontal translation, that happens when you add or subtract things from the x. And then our first rule was a vertical translation. That happens when you add and subtract things to the whole equation, right? And that takes care of our notes on the transformations of exponential functions. Thank you for watching. Have a good one.